Okay, welcome back. Should be half an hour later, and you should be very frustrated. Very frustrated and annoyed. There should be some that kind of jumped out at you, that you looked at, and I'm hoping that during the discussions, people will be able to explain to each other, oh, it has to be this, or oh, it has to be that, and kind of helping each other out along the way. It is a very powerful activity. I really like doing that and kind of working together to try to change each other's mind. But I'm sure there's some, maybe even quite a few, that you either disagreed on or you just maybe had no idea about at all. So very frustrating activity, I know. Now let's go over it. So I'm going to go over this, and I'm going to give you the answer key to this. All right, here we go. All right. Now, I wish I was there so we could argue and talk about these things, but I'm not. So, unfortunately, you're just going to have to take my word for all the answers here. All right, so the first one. If f is increasing, then f prime, the first derivative, is what? Well, then the first derivative is going to be greater than 0. It's going to be positive. And if you wrote the word positive in there, that's fine as well. If the first derivative is negative, the first derivative is negative if f is what? If f is decreasing. The second derivative is positive if the function is what? Concave up. The second derivative is negative if the original function is what? Concave down. Number 5. If f is concave down, then the first derivative is what? Decreasing. Be careful about using the words positive or negative there. I want you to think about it as decreasing. Number 6. If the first derivative, f prime, is increasing, then the second derivative is what? Well, the second derivative would be greater than 0. Number 7. If the first derivative is decreasing, then the function is doing what? Concave down. And again, remember, this tells me the kind of the curve. Does the curve look like this, or does the curve look like that? Number 8. If f has a horizontal asymptote at the first derivative, if f has a horizontal asymptote, then the first derivative has what? Has a horizontal asymptote at 0. At 0. So for number 8, the horizontal asymptote at 0. Number 9, if the first derivative is less than 0 and the second derivative is less than 0, then what does the function look like? It's going to be concave down, and we also know that since the first derivative is less than 0, second derivative less than 0, not only do we know that it's concave down, but it's concave down and decreasing. Number 10, if the slope of the function is increasing, then f is what? Concave up. Number 11. If the function is increasing, then the second derivative is what? Positive. Or positive. And here you could have written positive, and here you could have written positive as well. Number 12. If the first derivative is constant, then what's the function doing? It's linear. If the first derivative is a constant like 4, then that's the slope. It's linear. like y equals mx plus b. It's going to be, the function is just a linear function. Oh, I know that was one of the ones that was a gotcha one. That one seemed very hard, but when you think about it, it's like, oh yeah, that one's kind of obvious, kind of frustrating there. Number 13, if the second derivative is constant and positive, then what can you tell me about the original function? Well, it's going to be concave up, and what else do I know? Concave up, and it's going to be a parabolic. Think about nice parabolic. It was one of the sketches on the little cheat sheet that I handed out. And you hold on to those, definitely hold on to those. Kind of has all the tests in one nice place. Number 14, if a function does not have a maximum or minimum, but the derivative has an x-intercept, then what do I know that the function has? Well, then it has to have a point of inflection. Think about something like x cubed. Number 15, f, a function, will not have an inflection point when the second derivative is 0 if f has what in it? If it has no concavity. What's a better way of saying that it has no concavity? I could say that the second derivative is equal to 0. It's only going to have one max or a min. And there's like a parabola, but there's not going to be any change in concavity. There's not going to be any concavity there. Number 16, if f has an inflection point, then f has a change in what? This is one I think we should all have understood. Concavity. And again, I want you to realize when we use these words, what does that mean? A change in concavity. What does that mean? Well, that means that the tangent lines might have been above the function, and then at the inflection point, now they're below the function. There's a change. The tangent lines go from being above to being below. That's a change in concavity. That's a very important characteristic of a graph. Number 17, if f has an inflection point, then the second derivative has a change in what? Well, it has a change in sign. Either from positive to negative or vice versa, from negative to positive. That's how I know that that's an inflection point. The second derivative is changing signs from positive to negative. The concavity is changing. That's the inflection point there. Number 18, if the first derivative changes signs and exists, then the function has what? Then it definitely either has to have a maximum point or some sort of minimum point. Now, do we know just from that information? No, we'd have to explore a little bit more, but if the derivative changes signs and does exist at some point, then that function has a maximum or a minimum there. I'd have to know what's the change in signs. Is the first derivative changing from positive to negative? If the slopes of the tangent lines are changing from positive to negative, then I'm going to have a maximum. Number 19. If the second derivative is positive on an interval, then the first derivative is blank on that interval. Well, increasing on that interval. And the function is concave up on that interval. If the second derivative is negative on an interval, then the first derivative would be decreasing on that interval, and the original function would be concave down on that interval. All right, so very frustrating, gosh, very difficult. Make sure you've got all the correct answers down. Look at it, think about it, talk about it. If we had some more time, certainly we would talk about some of these ones. Which ones gave you a hard time? Which ones were frustrating? But we're moving on. We've got one more timed activity that I want to do. You might be able to guess what this next activity is going to be. Pop quiz. All right, so here's the quiz, and as soon as we shut down the video, we'll hand out the quiz and we'll start the quiz. But before we do, I just want to kind of go over it, take a quick look at it. So question 1, use the first derivative to find any critical values here. You just have to find the critical values. You don't have to tell me maximums or minimums or inflection points. Just find the critical values. Number 2, find the value C that satisfies the mean value theorem for that function over that interval. Now remember, the quizzes are going to be open notes. You can use your notes on this. We should have some good examples of this in our notes. And how do we do that? Make sure you organize your work very nicely. And the final answer here is, what is that C value? Number 3, given this different function here, f of x equals this, I want you to use the first and the second derivative tests to find the minimum, maximum, inflection points, and intervals where f of x is increasing, decreasing, and intervals where it's concave up and concave down. You must show first and second derivative tests. I want to see the tests here. The first derivative test, second derivative test, and then put all your answers in here. Once you've done the tests, read the tests, and then you should be able to give me all the answers based on the answers to the tests. And I want to see the different tests here. Flip it over. It does have a back side to it. For number 4, we're going to use the graph of y equals f of x below. Here it is. To determine the following. Select your answers from A through L given below. Estimate where the first derivative is equal to 0, and here I've got A through L are my answers. So don't put a number in here. Say, oh, I think the answer is H. So you're going to put an H here. And for the next one, oh, I think that's G. So I'm going to put a G there. And just put the letters that you think are in here. Looking at this, here is the scale, here's the function, and this is what I want you to do. We're estimating, and what are going to be my answers here. And then the final part, the final question here, in the left column below, in this column right here, are several functions. In the right-hand column, in different order now, are the graphs of the derivatives. And I want you to match them up. So this function, if I took the derivative of this function, which one would it match up with over here? So I've got, if we make this a little bit easier, this is function I, V, and V. And what I'd like you to do is over here, put the answers. So I want you to put your answers. Which derivative do you think is it here? Which one of these is the derivative? If you think the answer is I, then put your answer here, I, and then circle it. Whatever you think the derivative is, put it there. Now you've got the rest of time in class to do this quiz quietly by yourself. It's open notes. Certainly you can use the first derivative cheat sheet test and all that other good stuff. Work on this quiz. You've got the rest of the time to do this. Good luck, and I will talk to you again tomorrow.